All right, so today is going to be the last day that we talk about in TP2 theories. And so far, we've done two things in TP2. So the first thing we did was we just studied when you can find INP patterns of a certain number of variables or a certain depth. And we basically proved that TP2, if it's witnessed at all, it will be witnessed by a formula in a single free variable, and also that burden is submultiplicative. And we thought about burden as some kind of rough approximation of dimension. So that's one aspect of the theory. And I think that proof is nice because you get to see, okay, how do you play around with the arrays and what kinds of things can you do with the arrays? So when you're thinking just about formulas and arrays, mutually indiscernible arrays, there are certain sort of manipulations that you can do to get other arrays, and we saw some of those. So that's useful. The second thing we're doing, though, is now we're going to sort of connect it to the theory of forking and dividing that we developed in detail over simple theories. So we're just going to try and push that to a broader context. And what we did last time was we proved that if a formula divides in TP2 theory, that will be witnessed by some Morley sequence in an invariant type. So that says that dividing is always witnessed by some Morley sequence, but what you don't know is that it's going to be witnessed by every Morley sequence. We constructed a particular one. If you recall, we constructed an indiscernible type. We realized this indiscernible type countably many times in a Morley sequence, and then that gave us a configuration that looked like this, where because it was indiscernible, if the zero column, which is a Morley sequence and an invariant type, was not inconsistent, then that meant that all the paths were consistent. However, the indiscernible type we took was an extension of a type of an indiscernible sequence that witnessed dividing, or k dividing for some k. And as a consequence, you're going to have some k such that all the rows are inconsistent. So what do you do when you realize this Morley sequence? If the formula dividing is not witnessed along the path through this type, then that means that you get an NTP2, or sorry, a TP2 array. So this is going to be the kind of thing that we push against again. But now we want to prove a second lemma connecting dividing to Morley sequences. So this one says, if a formula divides, that'll be witnessed by some Morley sequence in a global M-invariant type. Now we want to look at a particular class of Morley sequences, the strict invariant Morley sequences, and say that if a formula divides, it's going to be witnessed by every strict invariant Morley sequence. And that's like a universal quantifier instead of an existential quantifier. And okay, that changes the flavor of the statement. This is going to be what's important to get an analog of Kim's lemma. So the important thing about Kim's lemma was that it converted dividing into a universal statement. So dividing is always existential. It says there is an indiscernible sequence that has the property that the formula is inconsistent along that sequence. Now, Kim's lemma converts that into a universal statement. It says that a formula divides if it's inconsistent along every Morley sequence. So what we did last time when we said that there is some Morley sequence didn't do that quantifier change, and so we need to get there. So let's just recall what a strict invariant Morley sequence is. I'll just go up to the definition since we did it last time. That is here. So a global M-invariant type is called strictly invariant or strict invariant over M if it's invariant one way. So it's a global M-invariant type. But also if I realize that type over a set of parameters, which I'm calling B here, then B is independent with A over M. And as we've discussed, in being an invariant, if you realize an invariant type over B, then the realization A will be independent with B over M, because invariant independence strengthens non-forking independence. However, the converse, the opposite direction, is generally not true. So this is like saying that you're in a situation where you have just this kind of taste of symmetry, just a hint of symmetry. You have non-forking both ways. Although in one way you have something a bit stronger than forking, you have invariance. All right, so this is a description of a certain kind of type, namely the strictly invariant global types. And if you realize a Morley sequence over M in that type, then what is it? It is a strict invariant Morley sequence. That makes sense. And notice that this is going to be a Morley sequence going one way and a Morley sequence going the other way because of strict invariance. But it's a bit more than that. I mean, but that's the idea. I mean, formally, what you should think of is that this is a way of recovering a certain degree of symmetry in a situation where forking in general will not be symmetric. Okay, so now the main lemma that we're going to prove first is that if you're in an NTP2 theory and you divide, then that will be witnessed by every strict invariant Morley sequence. And that's like Kim's lemma. The problem is we have no reason to believe that strict invariant Morley sequences exist. I've already told you that, outside of simple theories, forking is not symmetric. Why in the world would you expect there to be strict invariant Morley sequences? So once we prove the lemma, saying that dividing is always witnessed along a strict invariant Morley sequence, we have a second task, which is that we have to prove that such sequences, or really such types, exist. And if we can do both of those things, then we get a Kim's lemma, and we can prove that forking equals dividing over models, just like we did in simple theories. So that's the outline. Okay, so let's get a fresh page, and we will do our lemma. So lemma. Oh no, I think my Apple Pencil might be dead. Let's see. Here I was yammering along, and I could have been charging it the whole time. I mean, fortunately, these things charge extremely quickly. I mean, I think maybe 30 seconds is enough to get through the lecture, but I think we have to kill 30 seconds now. Okay, anyway. Okay, while we're waiting, are there any questions that people wanted to ask, by the way? About anything? No? All right. Well, let's see how we're doing. Okay, so lemma. So suppose T is in TP2. Then if phi x a divides over a model M of your theory, then for any strict invariant Morley sequence, a bar, which is ai I less than omega, over m phi x ai I less than omega is inconsistent. Okay, so this says that if you have a formula that divides, that dividing is witnessed along every strict invariant Morley sequence. These say the same thing. All right, so how do we prove this? As always, we sort of go into this proof asking ourselves what we have to push against. And the only real assumption that we have here is that the theory is in TP2. So the game will be that we assume that it's false, and we try to construct the TP2 array. That's how these proofs go. So so what we'll do is we'll say, okay, suppose not. Suppose Q extending the type of A over M is a strict invariant, strict M invariant global type, such that Morley sequences over M in Q do not witness that phi xa divides. Okay, so this is our start. Now, now what we'll do is we will say, let what do we want to call it? I guess we will call it a bar 0, which is going to be a 0j, j less than omega, be an indiscernible sequence with a0j, sorry, a00 is equal to a, such that phi x a0j, j less than omega, is inconsistent. Why can we do this? I mean, why do we know that there is such a thing? This is from our assumption that phi x a divides, right? So we know that we have a formula that divides, so that's going to be witnessed by some sequence, which we're going to call a bar 0. But we also were given the information that the formula is going to be consistent along Morley sequences in Q. So what we'll do next is we will let A1 realize Q over M and A bar 0. Okay, so then by M invariance, A bar 0 is M A1 indiscernible. And by strictness, we know that A bar 0 is non-forking independent over M with A1. So this is because when you have a strict invariant type, you get non-forking independence going the other way. So what we will do is we will let A bar 1 be some sequence with the same type as A bar 0 with A1 0, is equal to A1. And without loss of generality, by this independence, we may assume that A bar 1 is M A bar 0 indiscernible. If you're non-forking independent, then in particular you're non-dividing independent. And what does non-dividing say? Non-dividing says that I can always upgrade the indiscernibility by moving by an automorphism. So as long as I'm willing to move by an automorphism over the base, I can actually assume that something which is indiscernible over the base is indiscernible over the base and the thing on the left-hand side. So what does this look like? So we've got A bar 0 and A bar 1. And what we know is that both of these rows are inconsistent because that's how A bar 0 was chosen. And we also said that A bar 1 realizes the same type as A bar 0 over M. So both of these rows are inconsistent. However, if I take any 2 points, one from each row, then that's the first 2 elements in a Morley sequence in Q. And so that has to be consistent. And then we continue. So what we will do is we will let A bar 2 realize Q over M A bar 0, A bar 1. So then by M invariance, somehow independently, we have that each A bar I is M A2 indiscernible. And by strictness, you have that, sorry, that should say AI. And by strictness, you have that A bar 1, A bar 2, sorry, A bar 0, A bar 1 is non-forking independent over M with A bar 2. And so you can pick A bar 2 that has the same type over M as A bar 0, it doesn't matter, such that A bar 2, or let me say it this way, A2 0 is equal to A2, and without loss of generality, A bar 2 is M A bar 0, A bar 1 indiscernible. This again uses independence. And now let's look at what we have. So now we've got 3 rows. Each one of these rows has the same type over M as A bar 0. So all these rows are going to be k inconsistent for some fixed k. But any one of the paths that I choose is going to be the first 3 elements in a Morley sequence in Q. And Morley sequences in Q give me something which is consistent. So continuing in this way, we can construct inductively an array aij, ij less than omega, such that, okay, 2 things happen. Well, such that phi witnesses, you know what it means. So phi witnesses TP2 via this array, aij, ij less than omega. So that's the proof. So I mean, of course, you can write this a bit more formally using induction, but I think this makes the idea clear enough. So we add one new point by realizing Q, and when we add that one new point, we know that that point will be consistent with any choice of one element out of the rows that we had previously constructed. By our assumption that the type Q has the property that Morley sequences generated in Q give me something which is consistent for phi. So that tells me that paths through my array that I'm building step by step will be consistent, but then every path realizes the same type over M as the, every row realizes the same type over M as the initial sequence that I took that witnessed that the formula divided. So as a consequence, we get that it's k consistent along each row, and that's exactly what it means to have k TP2. So it follows that, you know, if you have this formula that doesn't divide with respect to such Morley sequences, then the theory has to have TP2. Okay. It turns out, in fact, that this lemma characterizes TP2, and that's kind of interesting fact. So if you have TP2, then you can find a model, you can find a strict invariant global type, such that the formula divides, but that's not witnessed by Morley sequences in that type. And that poses an interesting problem about, okay, how do you construct a strict invariant Morley sequence, you know, a strict invariant global type with this property? So I don't think we will do it in this class, but it's like a nice thing to think about, because it's not obvious how to construct such types. Okay, so that was the first step, and this gives us a Kam's lemma, provided that we can prove that such types exist. And so that's what we will do next. And the lemma that I'm going to prove now is going to be something called the vacuum cleaner lemma, which is kind of funny. So this is the vacuum cleaner. This is not my name. Sorry. Vacuum has 1 U and 2 U's. Sorry, 1 C and 2 U's, vacuum cleaner. So the story is, this lemma was proved in a paper of Artem Chernikov and Itai Kaplan, and they had a lemma which they called the Broom Lemma, which was very, very complicated. And I mean, I think the proof is like 2.5 pages of kind of complicated inductions and combinatorial manipulations of formulas. And the proof seemed like a very technical, I mean, the word that people had used to describe it was a technical tour de force. I mean, it seemed like a lot was going on. And I mean, a lot was going on. But later, there was another model theorist named Hans Adler, who found a simpler presentation of the same conclusion, and as a consequence, drastically simplify the proof that forking equals dividing over models in TP2 theories. I mean, it wasn't that it was a fundamentally different proof, but in some sense, he just distilled the basic thing that was going on and sort of presented the ideas in a different way. So this is very close to what I'm presenting today. But because it was somehow like a broom lemma, but improved, it became the vacuum cleaner lemma. Although I don't know that anyone else calls it that. I'm just saying that Adler certainly pushed this name. Okay, so that's why it's called that. And the statement is quite strange, but you'll see that somehow it's exactly what you need for proving existence of these sequences. So let's write the statement. So assume T is in TP2, and let P of X be a partial type that is invariant over M, which is a model of T. Okay, so we haven't actually said yet what it means for a partial type to be invariant, but in fact, the definition that we have makes sense. So what I'm saying here is that if I have a type over any set, I can of course consider it as a partial type over the monster model. And what does it mean for a partial type to be invariant? What it really means is that, you have these two versions, right? Either if I replace a parameter with something that has the same type, then that still goes in the type. Or that if I move the type by an automorphism, that that preserves the type. So another way of seeing this is that if I take any automorphism of the monster model, which fixes M, and I take a realization of my type, then the image under this automorphism should also be a realization of the type. So that for me is maybe the most concrete way of seeing it. Take any realization of the type inside the monster model, take any automorphism which fixes M pointwise, then take that automorphism will take a realization of the type to another realization of the type. So there's no way of leaving the type by applying an automorphism over M. So that for us is what invariance will mean. Okay, so good. Well, yeah, I guess that's fine. But I think it's important that if you contain a positive instance of the formula, I should be careful here. If you contain a positive instance of a formula like phi xc, then for any automorphism sigma, which fixes M pointwise, phi x sigma of c should also be in the type. You can't just have like a very incomplete type, because if you did that, then of course this fact about moving realizations would still be true, but then it wouldn't be enough. So you'll see where this comes up. We just need to know that basically what we need to know is that if you have a formula like phi x b, which is implied by our type, if we replace b with b prime, which has the same type, then the type should also imply phi x b prime. Okay, so we'll see where this comes up in the proof. But anyway, invariant means what you think it means, provided that you think the right thing. And let's suppose that P of X implies CXB, or a disjunction of some in formulas, which we will call phi superscript I x c. So these all have the same parameter, which is called c, where B is invariant independent over M with C, and each phi I x c divides over M. So you have a kind of funny situation. You have a type P, which implies a disjunction of a formula C and a disjunction of dividing formulas. What this will say is that then actually the type has to tell you which disjunct. It has to tell you that it satisfies CXB. Sorry. So if you imply a disjunction of a formula and a bunch of dividing formulas, provided that the parameters are in a certain configuration, you have to actually imply the formula that wasn't among the dividing formulas. So this somehow says you avoid a disjunction of dividing formulas. You have to be in, remember that dividing formulas you should think of as somehow small. And what this is saying is that if you have a type which is an invariant partial type, and you have a disjunction where the parameters of the formulas are in a certain configuration, then you'll avoid the dividing formulas. So this is a very technical kind of thing. So if it doesn't seem to look natural to you, then that's fine, that's normal. But you'll see in just a moment that this is exactly what we need to prove existence. Okay, and the proof is kind of funky. So let's see how it goes. So we'll start. I mean, so the proof will be by induction on n. Where n, as you see here, is the number of dividing formulas. So we're going to take a disjunction on the number of dividing formulas. And clearly, if n is equal to 0, then how many dividing formulas do we have? We have none. So in that case, our assumption just says that P implies CXB, and our conclusion says that P implies CXB, and that follows from our assumption. So in that case, we're good. So there's nothing to show in the case that n equals 0. That one is trivial, as it should be. I recently gave an exam. I guess like 3 weeks ago, I gave an exam in my discrete math class, and one of the problems was to show that if you have, let's say, some number of sets, let's say a1 through an, where n is at least 2, and you take the product of their union with another set, that's the same thing as taking the union of the products. And actually, this is a funny induction because the only non-trivial part of it is the base case. So you prove it for 2 sets, and that you have to do like a little set theoretic argument, and then for the induction step, it follows formally. And this was really baffling to my students that you can have an induction where the induction step is trivial, but the base case is hard. Or, okay, non-trivial. And I don't know. So now every time we get an induction where it's like a base case is trivial and then the rest is complicated, I feel like satisfied. It's like, oh yeah, the world is as it should be. Okay, that's a completely irrelevant aside. Okay, so where are we? So now we assume for n. And what we will do is we will assume that Px implies Cxb, or a disjunction of I less than n plus 1 phi I x c, where, okay, what do we need to assume? We assume that B is invariant independent with C over M. Recall that means that the type of B over MC extends to a global M invariant type. And each phi I x c divides over M. So far, so good. So what we will do is we will let Ci, I less than omega, be a Morley sequence. In a global M invariant type that witnesses that our nth formula, or sorry, our n plus first formula, phi n x c divides. So this is something we can do by lemma from last time. Okay, and we can assume, so let's call this C bar, just to give ourselves some notation. We can assume that B is invariant independent over all of C bar. Why? Well, because there's some global M invariant type, Q, such that B realizes Q over MC, just realize Q over MC bar. Then B will have the same type over C as it did before, but now it's invariant independent over everything. So this is very easy to arrange. You can arrange that it's not just invariant independent over C, but over the entire sequence. So far so good. And notice that it follows. That's not how you write follows. Follows by M invariance that C bar is MB indiscernible. We've used this principle a few times. If you have an M indiscernible sequence and you realize a global M invariant type over that indiscernible sequence, then that indiscernible sequence is not just M indiscernible, but it's indiscernible over M together with the realization, which is easy to check by hand. All right, so far so good. Now, the invariance of P entails that P of X will imply CXB, or now I take a conjunction over I less than K of, or no, sorry, let's make this J less than K of the disjunction of I less than N plus 1 of phi I X C J for any K. Okay, why? Well, what happens if I just look at J equals 0? So if I look at J equals 0, then what do I know? That realizes the same type as BC. So I know that BC0 has the same type as BC. So P of X implies CXB, or the disjunction of the phi i's with C0. But I know that BC1 also has the same type as BC0, which also has the same type as BC. So P by invariance will again imply CXB, or the disjunction of phi I X C1, because it has the same type, and my type is invariant. Again, it's going to do the same thing for the disjunction of the phis with C2, or C3, or C4, or C5. So if I look at any finite number, I know that I have to imply the conjunction of all of those things. So I imply CXB, or the conjunction of the disjunction where I replace the parameter with any parameter from my sequence. So I could look at the first K, and I have to imply the conjunction of the disjunction with those first K parameters in this place. So we have to imply all of these things. This just follows from the invariance of our type. Because we imply the first disjunct, we have to imply the second disjunct because it has the same type. And because we imply the second disjunct, we have to imply the third disjunct because it has the same type. Okay, cool. But if K is large enough, such that phi in X Cj for J less than K is inconsistent, then P of X will imply CXB, or the disjunction over all I less than N and J less than K of phi I X Cj. Let's think about why. This is really just like propositional logic now. So we know that we imply CXB and the conjunction of these disjunctions. So the question that you should ask yourself is it possible that if I choose a realization of P of X, that what is going to be satisfied will be the nth disjunct in every one of these conjuncts? So I look at this conjunction of K formulas. Is it possible that I pick the nth disjunct in each one of these disjuncts? So that would mean I satisfy phi in x c0, phi in x c1, phi in x c2, phi in x c3, and so on and so forth, all the way up to ck minus 1. Is that possible? Well, no, because I assumed that k was large enough such that the sequence was inconsistent. Recall that I took the CIs to be a sequence that witnessed that this formula divides. So it's going to be inconsistent along that sequence by compactness. I'll see that at some finite stage. So what happens at that point is I know that I can't satisfy all of these nth disjuncts. So what does that mean? It means that I have to satisfy some of the other disjuncts. So what does that look like? It means that I satisfy for some I less than n and some j less than k, one of the other disjuncts. Okay, this is just propositional logic now. So we get there, but then we start thinking about some of the properties of invariance independence. So what we know is that okay, so for each j, we have B is invariant independent over M with C, C greater than or equal to j. It's independent with the whole sequence, so in particular over C greater than or equal to j. And so this implies B is invariant independent over MC greater than j of Cj. This is like by base monotonicity for invariance independence, which is clear. If you're invariant over a small base, then you're invariant over any one of its supersets. And we also know that C greater than j is invariant independent over M with Cj, because C greater than j realizes like q to the omega over Cj. I mean, it came from a Morley sequence in some global M invariant type. So certainly we have this. So this and this together will imply by left transitivity that BC greater than j is invariant independent over M with Cj for all j. So it follows by the inductive hypothesis that since P of x implies, I'm going to write it in a suggestive way. So we have like C x b, or the disjunction over 1 less than or equal to j less than k, the disjunction of I less than n, phi I x c j, or, okay, I'm really sorry about this. This is kind of technical, I know, but or I less than n, phi I x c0. Okay, so let's just look at this for a second. All I did was I rewrote what I had above. So we had this thing here, and I've simply rewritten it in this funny way. So I separated the disjuncts that involve Cj for j greater than 0 with the disjunct that involves C0. So I just separated them. I've just rewritten. But now we note, and we know that B C greater than 0 is invariant independent over M with C0. So now I'm in exactly the situation that I have a formula, a disjunction of dividing formulas. The parameters are invariant independent, and I have an invariant partial type that implies this disjunction. What does that mean? The partial type has to imply the disjunction that isn't the disjunction of dividing formulas. So it follows that P of x implies CXB, or now I look at the disjunction of j less than k, phi I x c j, where this now is like I over n. Okay, so what did I do? I reduced the number of disjuncts by 1. But again, I can rewrite this in a suggestive way. I can rewrite this as P implies, in parentheses, CXB, or the disjunction of 2 less than or equal to J less than K, phi I. Okay, now I'm ranging over I less than N, X, C, J, or, and then I look at the disjunction over I less than N of phi I, X, C, 2. Again, I just rewrote it to pick off one of the disjuncts. And since B, C greater than 2 is invariant independent over M with C2, my inductive hypothesis will imply that, in fact, P of X proves CXB, or the disjunction of 2 less than or equal to J less than K of this disjunction I less than N, phi I, X, C, J. So continue. K minus 2 more times, and we obtain that P of X implies the disjunction of CXB, because that's exactly what you want. At a certain point, you get rid of all of these disjunctions, just iterating this argument K many times. Great. So, okay, that proves the lemma. So we've proved the vacuum cleaner. And I think that this is like a really funky argument. Like, you know, it's weird. You have to apply the inductive argument, inductive hypothesis to like some crazy looking disjunct, and it works. So I mean, this is a really nice argument that I think I wouldn't have thought of it. So all right. So an immediate corollary, which is nice, is assume T is in TP2. Then a consistent partial type invariant over M does not fork over M. Okay, why? So proof. So take CXB to be the formula that says X is not equal to X. So suppose you have a partial type, which is invariant over M, and it implies a disjunction of formulas that divide. That's what it means for the partial type to fork. Then in particular, it implies the disjunction of the false formula, X is not equal to X, and that disjunction of formulas that divide. But then this lemma says that, in fact, the type has to imply X equals X. It can't imply the dividing formulas, but that contradicts the fact that it's consistent. Okay, so an immediate corollary is just this thing. But now let's prove the existence. So let's do our existence lemma. Which is going to be the last thing we do today. So let's assume T is in TP2. Then every type over a model has a strict invariant global extension. Okay, so how do we prove this? So we're going to start with, so let P be a type over some model. So we fix a model of our theory, and we take some type over that model in the variable X. And what we'll do is we will just look at the following partial type. So consider the collection of formulas which is going to be, okay, we have the type, we want to say that it's invariant. So what do you have to say that you're invariant? You say C x C if and only if C x C prime, as C and C prime range over tuples in the monster model, which have the same type over M. So this is a collection of formulas that if you satisfy them, you'll be invariant. This is the sort of invariant schema so you have to satisfy. But then we want to be strict. So what does that mean? That means that the parameters should be non-forking independent with the realization. So what we will do is we will look at not phi x b such that there exists some a which realizes p, and I could have instead said for all, because this is an invariant property, such that phi a y, so now I think about this as a formula in the variable y with parameter a, forks over m. So this is saying that the parameter b is independent with the realization in the other way, right? Notice that we sort of flipped the role of object and parameter here. So if consistent, then any completion will be the desired type. So what do we have to do? We just have to show that this is consistent. So suppose not consistent.
Okay, Nick,
Yeah.
this doesn't quite compile. I think you should put either the phi a and b holds or something.
I should put what?
You should add that phi a and b holds. I think. I mean, what is b?
Oh, so b is any parameter ranging over the monster model. So I'm just looking at all formulas. Oh no, I see what you're saying. So wait. No, I think what I'm saying is right. So I look at all parameters, and I'm saying that none of them will satisfy a formula which forks when I use a realization of my type as a parameter. So I want to say that phi a b doesn't hold, right? Like the point is, so suppose I take some completion. So suppose I take some a which realizes this partial type. But there's some parameter b living somewhere in the monster model such that b is not forking independent over m with a. So what happens in that case? In that case, there's some formula. So it follows that there's some formula phi ba, which is true, and phi ya forks over m. And that's something which contradicts the way that the type was defined. Because the type was defined to include the negation of all formulas which fork when the parameter is a realization of the type P. Does that make sense?
Yes, okay.
Okay, good. Great. So so all we have to do is show that this is consistent. Why is it consistent? Well, if not consistent, then P of X will imply a disjunction of the form phi xb, or a disjunction of some in formulas, which say not CIX, CI if and only if not, sorry, if and only if CIX, CI. So this is just saying if it's not true, then you have to imply a disjunction of the negations from those things, and that's what this looks like. this should have like a prime moment where phi ay forks for some / all realizations a satisfying p, and ci has the same type over m as ci prime for all I less than n. Okay, so since phi a y forks over m, in particular, q of y, which is just going to be this partial type I get when I look at phi a prime y as a prime ranges over all tuples inside the monster that have the same type over a. This also forks over m. And is m invariant. Right? I mean, all I did was I took a formula that forked and I added a whole bunch of other stuff. So of course that is still going to fork. But that implies that it's inconsistent by the corollary. We proved before that that an invariant global partial type cannot fork over the set over which it's invariant. So this can't be consistent. It can't be a type. So what we'll do is we will let a0 through am minus 1 realize p be such that phi x ai I less than m is inconsistent. We know that q, I mean, this collection of formulas is inconsistent, so I can take finite limini that are inconsistent. That looks like this. Then let p in the variables x0 through xm minus 1 be an extension of the type of a0 through am minus 1 over m, which is global m invariant. Great. So it follows that if I look at just the restriction of p to the variable xj, so I just look at one of the variables at a time, that of course extends p. So this implies phi xj b, or a disjunction of I less than n of not ci x ci if and only if ci x c prime I. P proved this, so the global type has to prove this because it extends p. This extends p. So sorry, I should put like a tilde here because it's extending the type that we chose. So by our assumption, it follows that p tilde restricted to xj implies phi xj b by the Broom Lemma. Sorry, the vacuum cleaner lemma. So since that was true for all j, we have that p tilde x0 through xm minus 1 implies phi x well, let me say it this way. It implies the conjunction over all j less than m of phi x j b but we knew that phi x0 b and dot 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 and phi x m minus 1 b is inconsistent because if I looked just at the type of a0 through am minus 1 over m, that implied it's not the case that there exists some y such that the conjunction over all I less than m, sorry, j less than m of phi x j y holds. That's how we chose it, right? We chose it such that we would have these m things that all had the same type as a, and jointly those instances of phi would be inconsistent. So that's part of the type of a0 through a minus 1, which is extended by p tilde. So if p tilde proves these things, then it violates the choice of these AIs. So that contradiction completes the compactness argument. So ultimately, this collection of formulas is consistent, and that means that we find a strict invariant Morley type. So we have all of the ingredients for Kim's lemma now. We know that if a formula divides, it's going to be witnessed along any Morley sequence in a strict invariant global type, and that tells you lots of stuff like forking equals dividing, and it tells you that you can understand dividing in some meaningful way. So we will sort of put together the pieces again when we discuss this on Wednesday. We'll formally state Kim's lemma. We will describe the implications. We'll give forking equals dividing as a corollary, but really the argument is done. In some sense, once we know both that dividing is always witnessed along strict invariant Morley sequences and that such sequences exist, we have converted dividing, the existential statement of dividing, that there exists an indiscernible sequence of a certain kind, with a universal statement that you're inconsistent along every Morley sequence of a certain kind. And that's a powerful tool in trying to understand what dividing looks like here. Okay, so I will stop there. Are there any questions?
Me?
Yeah.
Okay, what was the original Broom lemma?
Yeah, so I haven't looked at it in something like 4 years, but I don't actually remember why it was so much more complicated. I mean, there was all this like moving around of sequences. Like they worked with arrays instead of um, just a single Morley sequence. I mean, I think maybe they took a Morley sequence in all of the tuples at once or some such thing. But honestly, it's been too long since I've looked at it, so I can't tell you. But I encourage you to look at the paper. I mean, the paper itself is quite nicely written. It's just a bit more complicated than it needed to be. And I mean, they prove some other things there, which are still maybe useful ideas. So this is the paper. I believe it's called Forking and Dividing in NTP2 Theories. It's in the JSL. I think it came out in 2008 or 2007. Anything else? No? Okay. Well, I'll see you all Wednesday. I just as a reminder, of course, like I know that okay, this year's weird, so maybe not everyone will be traveling or spending time with family on Thanksgiving, but you know, the classes are recorded, so don't feel any pressure to come on Wednesday. I mean, I will be giving the lecture like normal, but you know, do take advantage of the videos if you want to both follow the course but also want to like eat pumpkin pie on Wednesday instead. So cool. So I will see you all Wednesday, either really or virtually.